This chart shows the solar radiation energy level over wavelength. The thicker line indicates the total solar radiation at outside atmosphere, and the thinner curve indicates the solar radiation at the surface of the Earth. Humans can only see a small portion of the solar radiation, the visible light spectrum, which is between 380 nanometers and 740 nanometers. Other portions, such as solar infrared and ultraviolet, have wavelength either too large or too small for us to see. When full spectrum light goes through a prism, it separates into colors because each color has a different range of wavelength. Violet has the shortest wavelength at around 400 nanometers, whereas red has the longest at around 7 nanometers. The human eye's spectral sensitivity varies depending on wavelength. An average human with normal eyesight is most sensitive to wavelength of 555 nanometers, which is in the range of green light. Therefore, compared to light at other wavelengths, green light produces the highest brightness impression to people. This dashed curve V lambda represents the human eye's spectral sensitivity level. The solid curve represents the physical daylight power intensity level over wavelength. Here, we're introducing four basic light measurements. The first two, luminance flux and luminance intensity, are measurements to characterize light sources. Luminance flux is the measurement of the total amount of visible light emitted by a light source. The SI unit of luminance flux is lumen. Luminance intensity measures the capacity of a light source to provide illumination in a given direction. Its SI unit is candela. Light sources providing the same luminance flux may produce different luminance intensities in different directions. The next two measurements, illuminance and luminance, can be confusing. In short, illuminance measures how much light falls onto a surface, whereas luminance measures how much light bounces off of a surface. Illuminance is a measurement of how much light a surface receives and is defined by the ratio between luminance flux, illumines falling on the surface, and the area of the surface. Its SI unit is lux. 1 lux is equal to 1 lumen per meter square. Luminance is a measurement of the amount of light emitting, passing through, or reflected from a surface. The luminance of such a surface is determined by the illuminance this surface receives and its reflectance. The SI unit of luminance is candela per meter square. When a piece of steel is heated at a lower temperature, the piece will glow a dark red color. As the temperature goes up, red turns to yellow, then white, bluish white, and finally blue. The color temperature of light sources, therefore, can be represented by the Kelvin temperature of the metal object. The higher the color temperature, the cooler the light. The lower the color temperature, the warmer the light. Color temperatures over 5000 K are called cool colors. Lower color temperatures are called warm colors. Typically, color temperatures for commercial and residential lighting applications fall somewhere on the scale of 2000 K to 6500 K. The light reaching our eyes from an object is a product of the surface property of the object and the spectral power distribution of the light illuminating the object. White light, such as daylight, is a mixture of all colors, full spectrum light. In this example, full spectrum light strikes the red apple. The surface of the apple only reflects the wavelength of red light to the human eyes. The rest are absorbed by the apple. The red light that enters the eyes strikes the inside surface of the eyes, where light sensing cells send a signal to the brain. The brain receives the signal and perceives the apple being red. When full spectrum light, such as daylight, strikes a white surface, all wavelengths of the light are reflected. The white surface therefore appears to be white. When full spectrum light strikes a red surface, only the red component is reflected. The red surface therefore appears to be red. When full spectrum light strikes a black surface, no light is reflected. The black surface appears to be black. When yellow light strikes a white surface that can reflect all wavelengths, the yellow light, which is the only component incident on the surface, is reflected. The white surface therefore appears to be yellow. When yellow light strikes a red surface, which can only reflect red wavelength, the yellow light is absorbed and no light is reflected. The red surface therefore appears to be black. When yellow light strikes a black surface, it is absorbed and no light is reflected. The black surface appears to be black. Therefore, only black and yellow objects will appear their true color under yellow light. To define how well a given color appears as rendered under a certain light source, the metric of color rendering index, CRI, is developed to measure a light source in terms of its ability to render the colors of visible elements in comparison with natural light. Light sources are assigned their places within the CRI index at a value between 0 and 100. Light sources at the higher end of the scale will produce a more accurate color rendering of the objects around it. Daylight has the highest CRI, 100, which makes it an excellent light source. Light that falls on a surface can be absorbed, transmitted, or reflected depending on the surface property. The absorption factor, absorptance, is the ratio of the absorbed light to the incident light. The transmission factor, transmittance, is the ratio of the transmitted light to the incident light. The reflection factor, reflectance, is the ratio of the reflected light to the incident light. All these factors are values between 0 and 1, and the sum of the three is always 1. When light strikes an opaque surface, the transmission factor is 0. Light is either reflected or absorbed. Light reflects from a smooth surface at the same angle as the angle of incidence. From a smooth surface, reflected light rays travel in the same direction. This is a specular reflection. From a rough surface, reflected light rays scatter in all directions. This is a diffuse reflection. Spread reflection is in between. Light is reflected into a cone of light rays, generally in one direction. When light traveling through a transparent medium hits a boundary with another medium, for example, from air to glass, a portion of the light is reflected, a portion is absorbed, and a portion is transmitted into the second medium. Light transmission can take place in three forms: direct, diffuse, and spread. In direct transmission, light passes through a material, such as clear glass, in a predictable path. In diffuse transmission, materials such as frosted glass or thin paper scatter the light rays as they pass through in random directions. Materials that allow for diffuse transmission are called translucent, as opposed to transparent in direct transmission. Spread transmission is in between. Light rays scatter but still maintain their general direction after passing through a material.